Equilibrium-1.host.com.
Okay, students, after the grand response from the all students for the my RRE series, that is Rapid Rank Enhancer series. We are into the next lecture. I have got a huge response from the most of the students for my first lesson about the states of matter in the Rapid Rank Enhancer series 1, where I will be completing one chapter in one shot, which makes you hero from the zero, because I will be covering from the very basic point, from the very basic. I will start teaching you from the basic as if you know nothing about that chapter, and I will be taking to your level of advanced level. So that is the advantage of this series, one chapter in one day. It must be used when we have the less time but more to study. So this is the best way to revise your entire chapter in one day as per the examination point of view, instead of reading books and not able to understand how the questions will be coming and how you have to prepare. All will be guided in one shot only. Okay. So we are in the RRE series second lecture, Rapid Rank Enhancer. Second lecture is on the equilibrium. Yesterday I got received some interested topics, that is among them the top is the equilibrium. So today we are going to complete the equilibrium in one shot. I think everybody is now ready to make a notes. I mostly say that the best notes in the world is the notes made by you as per your requirement and as per your convenience. Okay, so you refer 10 books, but the way you when you revise it from your own notes, then the understanding will be different. Okay, so try to be with me. Some students asked, sir, video lengths are very much high, we are not able to make it concentrate up to that time. For them, I cannot reduce my content. I don't want that any point I should miss from the chapter, so that if that question comes on the basis of that chapter, you should lose marks. Okay, so if the content is around, I am trying to make the total chapter in 1 hour, and if you are not able to concentrate till 1 hour, then what you will be doing, you will pause it there itself, take some rest, and then you can come back with the same energy. The energy and attentiveness should be maintained from the beginning to the last. Okay, and from today onwards, I am going to give you my handwritten notes and some notes also, and how you are to approach me, how you have to get that, I will be telling you in the future time. Okay, so are you ready with me? Equilibrium in one shot in RRE series second lecture, that is which makes you from zero to hero, or it makes hero from the zero. Okay, so the very basic topic I will be starting, and I will be taking you to the very advanced level. Are you with me? Are you ready with pen and attentiveness, notebook, and see here, equilibrium. Okay, chapter name is equilibrium. So right from the basics, chemical reactions are divided into two types, which are called as reversible and irreversible. Okay, which are called as reversible and irreversible. So reversible reactions means the reactions which the reactions in which reactants the reactions in which reactants can form product. At the same time, product can recombine to give you the reactants back. Such reactions are called as reversible reactions. Okay, in some cases what happens, the product may not recombine at the condition, at that temperature, at that pressure, at that volume. They may not be able to recombine. At higher temperature they may combine, at higher pressure they may combine, but at that particular conditions, if they do not able to recombine to give the reactant back, then such reactions are called as irreversible reaction. Okay, so the questions are coming, which of the following is a reversible reaction? Which of the following is a irreversible reaction? How to identify them? Sir, we are getting confusion. Okay, so as I teach in class and I can come to know the difficulties faced by the students while attempting the questions. So I will be making some tips then according to the problems faced by the students. That is the difference between the my lecture and studying from a book. Okay, so the to understand which of the following is reversible, which of the following is irreversible, only single two tips are there. First, if any of the reactants or products are in gaseous and the reaction is carried out in open container, so they will escape after the formation of product, they will escape, so they cannot recombine with each other. That's why it has to be reversible. If a reaction is carried out in open container and products are in gaseous state, then the reaction is going to be irreversible. And if any of the product is precipitated, that means it is taken away. It is taken away, then the reaction also will be irreversible. So tips to identify irreversible reaction from a reaction, irreversible reaction. What is the tip? If gaseous products are there and open container is mentioned, then it is going to be irreversible. If precipitate is formed, so it will not come back to the solution and it will not react. That's why it is also irreversible. Okay, so in the reversible, the it should be carried out in closed container and no precipitate formation should be there. Okay, if all reactant, if all reactant and products are in the same physical state, then it is called as homogeneous. If any one of them, at least reactant, at least one product is in the different physical state, then it is called as a heterogeneous equilibrium. Okay, so this is the first segment. Okay, now we are in the next segment after studying the types of reactions. Types of reactions, reversible and irreversible, and in reversible, homogeneous and heterogeneous. Coming to the next segment, in the reversible reaction, there is a state. This is that state is called as a equilibrium. Okay, equilibrium is a state of reaction. Equilibrium is a state of reaction where the one major condition it should follow is forward reaction and backward reaction. In a reversible reaction, there will be two reactions, forward reaction and backward reaction. If they both occurs at the same speed, the speed at which the forward reaction occurs, at the same time backward reaction also should occur, then that condition of a reversible reaction is called as a equilibrium. Be careful, the equilibrium cannot be present in a irreversible because there is no backward reaction at all. Okay, so in the equilibrium also it is not, equilibrium is not at every condition of the reversible reaction. In a reversible reaction, only if this condition is satisfied, then that state is only called as a equilibrium. Okay, so this equilibrium is further divided into basically two types. Basically, how many types? Two types. First one is called physical equilibria, second one is called chemical equilibria. Physical equilibria means reactant and product side formula will be same. Chemical nature of the reactant and product will be same, but what is changing? Physical nature. What is the physical nature? That will come to know. Okay, the chemical formula of the product, chemical formula of the reactant, if both are different, then they are called as a chemical equilibria. Then it is called as what? Chemical equilibria. Okay, and chemical equilibria further divided into two types, molecular equilibrium and ionic equilibrium. Like ammonia decomposed. Okay, 2NH3 reversible and 2 plus 3H2. Here reactant and products are entirely different. Chemically it is ammonia, it is nitrogen, it is hydrogen. Chemical formula itself different, and all reactant and products are in molecular state, then that type of equilibrium is called as a molecular equilibrium. If the similar, suppose let us take acetic acid. Okay, so acetic acid dissociates. I am writing it here, dissociates to give CH3COO minus plus H plus. So it is consisting of ions. It is also reversible reaction, but it contains ions. Then it is called as a ionic equilibrium. Okay. So that chemical equilibrium part, is it understood? Okay. That means the reactions in which product is different from the reactant. Molecular formula and chemical nature of product is different from the reactant. Then it is called as a chemical equilibria, further divided into two types, molecular equilibria and ionic equilibria. These are some examples. Okay. Now let us study about the physical equilibria. Okay. So one by one I will be explaining. SL means solid liquid equilibria. Okay. So let us take water. It is in the solid state, water in the liquid state. So chemically both are water only. Okay. But what is different? Physical state is different. Okay. So this direction it is called as a melting. This direction is called as a freezing. Okay. So there will be two reactions. Forward reaction is called as melting and backward reaction is called as freezing. Backward reaction is called as what? Freezing. Okay. Forward and backward both are different. Okay. So the reaction at which rate of melting, the reaction at which rate of melting is equal to rate of freezing. So that condition of this reversible reaction is called as a solid liquid equilibrium. Okay. So if 10 molecules are converted from solid to liquid, at the same times 10 molecules of liquid should be converted to solid. So this is the condition and it takes place at freezing point. It takes place at what? Freezing point. So this is about the solid liquid equilibrium. Then liquid gas equilibrium, very simple. Here it will be in liquid and it will be in gases. Okay, it will be in gases. In this condition, liquid to gas, it is called as, if it is converted from liquid to gas, okay, then it is called as evaporation. Okay, evaporation, sometimes it can also be called as boiling. Okay, and gas to liquid, it is called as condensation. Gas to liquid, it is called as what? Condensation. Okay, so that means rate of evaporation should be equal to rate of, very good, rate of evaporation should be equal to rate of condensation. That is called as a equilibria. Okay, so and what is the condition? It takes place at the boiling point. It takes place at what? Boiling point. Next, coming to the solid gas equilibria. Okay, so it is found only in the sublimate like iodine, camphor. What are the example? Iodine and camphor. Okay, so Ci2, actually in these compounds what happens, melting point is higher than the boiling point. Before they melt, they boil, they directly converted to gaseous state. Okay, so I2 solid to gas, this is called as sublimation. What it is called as? Forward reaction is sublimation, backward reaction is, sometimes it is called desublimation. In some books it is also given as condensation. It is given as what? Condensation. Okay, so at equilibrium rate of, okay, at equilibrium rate of sublimation must be equal to rate of desublimation. Okay, and it takes place below melting point. It takes place below melting point. Okay, so all these three clear. Then coming to the solid solution equilibria. Okay, solid solution equilibria, this will takes place at freezing point, this will takes place at boiling point, and this will takes place below melting point. Coming to the solid solution equilibria. Okay, so for this what we have to take? We have to take a saturated solution. Solid solution equilibria takes place in saturated solution. Okay, and how you will confirm that it is a saturated? There should be some substance lying at the bottom. Okay, so the same substance also available in the solution and same substance also available in the precipitate also, condensed also. Okay, so this is called as dissolution, this is called as precipitation. Okay, so conversion of a liquid from the solution to the bottom, it is called precipitation, and this is called as a dissolution. Okay, so solid solution, this is solid, this is a solution. Okay, this is solid, this is a solution. So rate of dissolution or rate of dissolving. Okay, rate of dissolution should be equal to rate of precipitation. Okay, this rate must be equal to this rate. Then it is called as a solid solution equilibria. Okay, and it is found where? In saturated solution. Okay, in unsaturated solution, only forward reaction, that is dissolution. In supersaturated reaction, only precipitation. But in saturated solution, both will be same. Okay, then gas solution equilibria. Okay, here solute is gaseous state. What is that? Solute is a gaseous state. Suppose CO2 we wanted to dissolve. When you keep on dissolving, some CO2 is in aqueous state and some CO2 is in gaseous state. Okay. So conversion of this to this, it is called as a evaporation, and conversion of this to this is called as a dissolution. Okay. So the state at which rate of dissolution is equal to rate of condensation is called as equilibrium, gas solution equilibria. It is found at a saturated pressure. Okay, at what pressure? At saturated pressure this will takes place. Is it understood? Are you ready for next segment? I think all of you are making a notes. If you're not able to make notes, then try to pause it and understand, then write. If still you don't want to write the notes, wait for my instructions in the future, some more time. Okay. Okay, now we are in the next segment of the graph questions. How to deal the graph question. Every concept is segregated as per the examination pattern. So if the question is about the graph pattern, then how to answer it. Okay. So there is a lot of confusion with what variable, how to draw the graph. Okay. This graph is by taking the time on x-axis and rate of reaction on the y-axis. Okay. So if the rate of reaction on the y-axis is taken, time on the x-axis is taken, always remember there will be only maximum two curves. How many curves? Two curves. Okay. So they both will be after certain point of time will become equal and constant. This is called as equilibrium time. What it is called as? Equilibrium time. After this, this is called as rate of forward reaction. What it is called as? Rate of forward reaction, and this is called as rate of backward reaction. Okay. So this is forward and this is backward. So after equilibrium, both are two things you have to remember. Both are constant, both are same. Okay. So when it is rate of reaction taken into account on the y-axis. Okay. If we are taking on the y-axis instead of rate of reaction, if we take the concentration, what we take? If we take the concentration, then this graph is also possible. Okay. So that time this variable will be changing. What is this variable is going to be? Now just understand. Okay. So initially what we have reactants only, we have products we don't have. So this is graph for the concentration of product. Okay, concentration of product. This is for the concentration of, sorry, this is concentration of reactants. Initially we have only reactants, and after that we will get product concentration initially will be how much? Zero. Initially concentration product will be zero, and at equilibrium initially concentration of reactant will be high. Both will be decreasing and may or may not be. This is only certain times happens. Okay, here concentration of both reactant and product are same and constant. Okay, but it may not be so every time. So there will be plenty of the graph. Okay, and it is not necessary that only two curves will be there. Suppose a reaction is there, A plus B gives C. Here three curves will be there. Okay, with reactants there will be two curves, with product there will be one curve. That means like this. Okay, one curve for A, another curve for B, and another curve for C. C is a product, will increase, reactant will decrease. Simple technique, simple tip. Whichever is coming from the top to bottom is reactant, which is going from bottom to top is a product. Okay. So number of top to bottom curves is equal to the number of reactant, and number of bottom to top will give you the number of product. Okay. Now let us take, as I told you, they may be constant or may be different. Okay. So if they are constant and equal, then equilibrium constant is going to be how much? 1. Okay. So let us take, this is a graph, and in the previous graph, if that is there, then equilibrium constant will be how much? It is going to be 1. Okay. So let us take like this. Okay. So here at after equilibrium, they become constant. Okay, but not equal. Constant but not equal. Okay, this is called as a equilibrium time. So at this condition, the equilibrium constant will contain product more than the reactant. Okay, this is for reactant, this is for what? Reactant, and this is for product. So products are more, so equilibrium constant case is going to be greater than 1. Okay, and if it is in the other condition, okay, in the other condition means product is less than the reactant. The third graph I am going to explain you. All will be drawn and given to you in the notes form, handwritten notes form. Okay, if you are not able to make it, okay, but I suggest you to write your own notes. Okay, I will suggest you to write your own notes. Let it be time taking, but it will be worthful. Okay. Here reactant concentration are more and product concentration is less. They are constant at equilibrium time. Okay. So in this condition, Kc will be less than 1. If they both meet, then Kc is equal to 1. Okay. So this is applicable only when 1 mole of reactant is there, 1 mole of product is there, and only one reactant, one product is there. Okay. So that is the difference between the graph. By taking concentration, three possibilities are there. They may be constant but not equal. They may be constant and reactant higher, product lower, and product higher, reactant lower. Okay. But if I write it here, rate of reaction, there will be only two curves and they will meet with each other and they will become constant at equilibrium. Okay. So these graph questions, I think everybody understood. Okay. So graph question, nobody should leave. Nobody should. Okay, we are into the next segment, law of mass action. After studying the three graphs, I think you are able to answer all questions related to graph. Now let us come back to the next segment, which relates with the formula derivation. And for that, some theory is required. That derivation is that theory is law of mass action. Okay, according to this, let us take A moles of A react with B moles of B to form C moles of C and D moles of D. Okay. So according to this reaction, rate of any reaction directly proportional to concentration of reactant to the power of constant coefficient, to the power of what? Coefficient. Okay. So this reaction, reversible reaction, is basically two reactions. This reaction is called as a forward reaction. This reaction is called as a backward reaction. During the forward reaction, this is reactant. During the backward reaction, this is reactant. Okay. So difference in the reactant and product for each reaction. If I talk about the forward, this will become reactant, this will become product. If I talk about the backward, this will become reactant and this will become as a product. Okay. So there are, as I told you, there are two reactions. I will be using this formula two times. One for the forward reaction, another for the backward reaction. Okay. RF, forward reaction. For forward reaction, these two are the reactant. RF is equal to K into A to the power of A and B to the power of B. And RB, backward reaction. For the backward reaction, these are the reactant. Therefore, KB, rate constant KB, C to the power of C and D to the power of D. Okay. So, but at equilibrium, for a condition of equilibrium, the main condition is rate of forward must be rate of backward. Okay. So, if I apply that, these two will be becoming equal. RF is equal to RB. So that means I can write it as a KF into concentration of A to the power of A and B to the power of B is equal to KB into C to the power of C and D to the power of D. Okay. So Kf upon Kb, Kf upon Kb. So all constants should be brought at one place and all concentration terms should be brought at another place. So Kf upon Kb, Kf upon Kb is going to give you C to the power of C and D to the power of D divided by A to the power of A and B to the power of B. Okay. So this is the derivation. This is the derivation for equilibrium constant. Kf upon Kb is equal to C to the power of C. As this is a two constant, this can also be written as new constant that is equal to Kc. Okay, so this is the term used here. Square bracket shows that it is a concentration. Okay, if the reactants are in solution state, this is the formula. Okay, but if the reactants and products are in gaseous state, then we use another formula called as Kp. Okay, Kc is equal to concentration of product, that is C to the power of C and D to the power of D divided by A to the power of A and B to the power of B. For the same reaction, if I write Kp, equilibrium constant Kp, then it is going to be, instead of square bracket, we will write it here partial pressure. What we will write? Partial pressure of C to the power of C, partial pressure of D to the power of D divided by partial pressure of A to the power of A, partial pressure of B to the power of B. Okay, so this, for the same reaction, both are possible. For the same reaction, both are possible. So if both are possible, there should be some relation between them. What is that relation? We are going to see it now. Okay, for the same reaction, if you find out Kp and Kc, okay, so Kp is equal to Kc into RT to the power of delta Ng. Okay, this is the relation between Kp and Kc. Always remember P and C, personal computer. P should come here, C should come here, and there should not be any negative sign here. Okay, PC positive. What you should remember as a memory technique. Okay, as a memory technique, PC, personal computer positive. Okay, because of this technique, you are going to get lot of marks. All options look same, but their answers will be different. Okay, so Kp is equal to Kc into RT to the power of plus delta Ng. Okay, and here Ng, delta Ng is equal to number of moles of gaseous product minus number of moles of gaseous reactant. Very carefully you have to see gaseous only. What it should be? Gaseous only you should select, because it is derived from the gaseous equation. It is derived from where? Gaseous equation. And Kp can be equal to Kc. Kp equal to Kc when this becomes 1. To become 1, this delta Ng must be 0. Okay. So that means gaseous moles of reactant must be equal to gaseous moles of product. Okay. So Kp can be greater than Kc when this is divided. Okay. Then you are going to get, suppose Kc into something, if you are getting Kp, okay, into, that means positive. So delta Ng should be greater than 0, or we can say delta Ng value must be positive. Okay, and Kp will be less than Kc when delta Ng less than 0. That means it is negative. Okay, that means it is negative. So that time what happens? Suppose minus 3. So we can write Kc by RT to the power of 3. So that means on dividing you are getting Kp. So Kp will be less than Kc. Okay, is it understood? So this is the relation between Kp and Kc, derivation of Kp and Kc. Okay. Okay, now we are in the next segment, how to find direction of reaction. Okay, how to find direction of reaction. Okay, so for that a term is there, reaction quotient QC, and it is not a different formula. Formula will be same. Concentration of C to the power of C, concentration of D to the power of D divided by concentration of A to the power of A and concentration of B to the power of B. So you should get doubt, why sir, then it is, what is the difference between Kc and Qc or Kp and Qp? Here at any point of time you can substitute in this formula, but for Kc you should ensure that the given values are at equilibrium. Okay, so if they are at equilibrium, if you are substituting it here, no problem. If they are not at equilibrium, if you are substituting in Kc, that is a problem. Okay, so this is applicable at any point of time. It is applicable at any point of time. I think all of you are making a notes, and whenever I'm telling you important, you make an underline of it, you put a star mark of it. If I give you some logic, you make a note of it. Okay, so this is the QC. Okay, now suppose QC is only to find out the direction of reaction. Suppose if QC is less than Kc, that means it has to reach to the Kc. So that means it will go in the forward direction. Which direction? Forward direction. It wanted to reach to the Kc. Okay. If suppose QC is greater than Kc, that means it could overcome. Already it crossed out the Kc, then it will should come back to meet the Kc. Okay, so come back means what? Backward reaction. Okay, if Kc is equal to Qc, then already at equilibrium, why it will go at in any direction? It will not go in any other direction. Okay, so if Qc, this you have to find out, this you will be given. If the find out value is less than the equilibrium value, then it will reach to the Kc by moving in the forward direction. If the given value is more than the Kc, then it will come back to gain that equilibrium, that is backward direction. If already at equilibrium, then it will not go anywhere. Already it is at the stable most equilibrium state. Okay. So after this, we are going to continue with the extent of reaction. Here, to reach the equilibrium, in which direction it is going, it is determined with the help of the QC. Okay, and with the help of the Kc, we can find out whether reaction is almost completed or yet to be completed, will complete or not. Okay, so suppose Kc is equal to 1. That means concentration of product is equal to concentration of reactant. Okay, so that means both are significant. Both are significant. That means 50% of reaction only completed. Okay, both reactant and product are significant. Suppose Kc is into something to the power of 10 to the power of 3 and more. Okay, that means product amount is very larger in comparison to reactant. Okay, so only product are significant. That means almost every reaction is carried out to prepare what? Product. So almost we are getting 10 to the power of 3 times or more time than the reactant. Okay, so that means products are significant. That means reaction is almost completed. Okay, so if Kc is value is near by 10 to the power of -3 or less than this, that means reactant are in more in quantity. Reactants are in more in quantity. That means reaction is not interested to go in the forward direction. There is a lot of things to do in the forward direction. Okay, and here both are equally stable. Here product are more stable. Here reactant are more stable. With the value of the Kc, we can assess the stability of the reactant and product. We can understand how much reaction of our aim reaction, how much of the product is yet formed, can also be determined. This is called as extent of reaction. Direction of reaction determined by Qc and extent of reaction determined by the Kc. Okay, higher the Kc value, higher is the extent of reaction. Lower the Kc value, lower is the extent of reaction. Okay. Okay, we are in the next segment. Value of the we are in the next segment. Value of the equilibrium constant depends on what quantities and how it can be changed. Okay, remember one thing: equilibrium constant appear to be directly proportional to concentration of product and inversely proportional to concentration of reactant. Okay, but it is not, because if product and reactant, they are going to manage with each other to keep this constant. Okay, If you change one thing, other is going to change, but ratio is going to be same value. Equilibrium constant does not depend on concentration, does not depend on pressure, does not depend on presence of catalyst, does not depend on volume. It depends only on three things. How many things? Three things. Direction of reaction and coefficients of the reaction, and third and most important is temperature. Okay. So if in this direction equilibrium constant is K, in the backward direction if you are starting, then it will be 1 by K. It is going to be 1 by K. If in this direction it is K and everything is multiplied by 2, then it is going to be K to the power of 2. And if in this direction equilibrium constant is K divided by 2, K to the power of 1 by 2. Okay. So like that, coefficient changes, equilibrium constant changes, direction changes, equilibrium constant changes, and third and most important thing is temperature. Okay. So this is the formula to find out new equilibrium constant if change in temperature takes place. Okay. So if temperature is increased from T1 to T2, and this is the enthalpy of reaction, this much amount of heat either released or required, then this is the formula. Always remember this formula, temperature must be converted and substituted in the Kelvin form only. Okay. So main question will be, if it is endothermic and temperature is increased, equilibrium constant is directly proportional and it is also going to increase. Okay. So, but next one is, if temperature is increased but reaction is exothermic, then equilibrium constant is going to decrease, inverse proportional. For exothermic reaction, equilibrium constant is inversely proportional. For endothermic reaction, equilibrium constant is directly proportional. This is how equilibrium constant depends on direction of reaction. When equation is reversed, equilibrium will be inversed. Equilibrium is multiplied to the power of, divided 1 by power of, and temperature value. These are the few factors on which equilibrium constant depends. Okay. So okay, we are into the advanced level segment. Okay, so this type of questions will be derived and asked. For that, I am giving you direct formula. In some books, it is given also, but people are not able to understand by reading itself. Okay, so here dissociation. Dissociation means one molecule dissociate into, split up into more than one. So this n will be greater than one. First thing, keep it in mind. Okay, the one molecule splitting into two or more than two, then only it is called as a dissociation. Okay, so in that condition you have to find out degree of dissociation alpha. Okay, so there are two molecular mass, theoretical molecular mass. Okay, so initially we will have only this one. So in exam they will give as a theoretical. Okay, and this they will give as a mixture, experimental, or observed. Okay, so these are the three things. Word, the what type of word they are using, where you have to substitute. This is the main problem. Okay, so initially only one mole will be there, therefore molecular mass will be less. Sorry, molecular mass will be more. Okay, n is equal to, okay, mass upon molecular mass. So number of moles increases, molecular mass decreases. So as we move from here to here, moles are changing. One mole is changing to n moles. So moles increases. Therefore, molecular mass will decrease. So the more reaction occurs in the forward direction, equilibrium mixture molecular mass will decrease. So on that basis, this alpha value can be determined. Theoretical molecular mass, that is reactant, minus molecular mass of equilibrium mixture, this total mixture it is available, divided by n minus 1 into molecular mass of this mixture. Okay, so molecular mass can also be written as 2 into vapor density. 2 here, 2 here, 2 here, common and cancel. Okay, so this D corresponds to theoretical and small d correspond to experimental, mixture, or observed. Okay, so this is how you will find out the relation between vapor density and degree of dissociation. Okay. Okay, so equilibrium constant, next segment is about the equilibrium constant and Gibbs free energy. Okay, so the total Gibbs free energy is equal to delta G naught plus RT ln QC. So it can be found at any given point of time. But if the reaction is at equilibrium, then this value will be zero. This value will be how much? Zero. If this is zero, this total is zero, this will come this side. That means delta G naught is equal to minus RT ln Kc. Okay. So there is some students are losing marks because of this. Okay. So ln is equal to 2.303 log. Whatever the table we use, they are of the 10 base logarithm, which is to be multiplied with 2.303. Then we are eligible to use that log table. So this formula can also be written as minus 2.303 RT into log Kc. Okay. So if it is not mentioned that the reaction is at equilibrium, then you should use this formula. If it is mentioned reaction is at equilibrium, then you will use this formula. At equilibrium, delta G is equal to 0, but not delta G naught. Delta G naught is in the standard condition. Delta G is at the equilibrium condition. Okay. So as I told you to prepare your own notes, I think you are keep on preparing your own notes. If not, then I will give you one way. You can take a screenshot and send it to me, that number. Then I will send a PDF to you. Where you have to send, that I'm going to say you at the end of the session. Okay. At the end of the session, I'm going to tell you how to get handwritten PDF, my handwritten PDF to you. Okay. So that this lecture should match with your notes. Okay. But I will suggest you to write your own notes and prepare well. Take a break if you're not getting interested till the last. Okay. But try to keep maintain that interest till the last. Try to watch the video till the last. Okay, now we are important. I told you to stay with me till the last because most important topics are yet to come. This is one of the important topic and one more topic also yet to come. So stay tuned and stay with me. So Lee-Chandler principle. When a system under equilibrium, statement wise I am explaining you. When a system under equilibrium is applied with stress, then the equilibrium will reaction will move in direction so that the stress must be nullified. The effect of stress must be made as a zero. The effect of stress, to make it as a zero, it will move in that direction. Here the stress are different types of stress. Okay. The first stress is concentration. Okay. What is the first stress? Concentration. If concentration of reactant, concentration of product, okay, can be changed means it can be increased, it can be decreased. Okay. So if the concentration of reactant increased, then equilibrium will shift in the direction of forward. Okay. If concentration of reactant decreased, then it will move in the direction of backward. Okay. If the concentration of reactant increased, then it will move in the backward direction, and it is going to be, if it is decreased, it is going to be in the forward direction. It is going to be in which direction? Forward direction. Okay. If you take more reactant, then it will move to decrease the concentration. The concentration will be decreased in the forward direction. In the forward direction, reactant consumed and product produced. That is opposite. Whatever you make it, reaction will make it in the opposite side, so that the effect of stress will be how much? Zero. Effect of stress is to be nullified. Okay. This is the first stress of the Lee-Chandler principle. Then coming to the temperature. Then coming to what? Temperature. Very too complicated. People are making it a complicated. Very simple. Okay. If you give heat, it will take heat. If you want heat, it will give you heat. Okay. So suppose if you increase the temperature, if you increase the temperature, that means you are giving heat. Okay, it will take heat. So the heat is absorbed. Heat is absorbed in which reaction? It will move in the endothermic direction. Okay. So for example, A plus B plus heat, reversible C plus D. So if we are heating this reaction, it will move in this direction, because if you are giving, it will take. It will do just opposite what you want. Okay. So suppose if the heat is in this here, that means it is exothermic. So in this direction it will come. In this direction, C plus D takes heat to give A plus B. Okay. Temperature increase, the reaction will shift in the endothermic. Don't worry about the forward, backward. So if you are giving, it will take. It will take in this direction. It will in this direction. It is producing. Okay. So temperature decreased, then it means exothermic. Okay. It is. It will shift in the exothermic direction. If you are decreasing temperature means you want heat. So then it will give heat. In this equation, it will go in the forward direction. Okay. So second effect of stress, I think all of you understood. Okay. Okay, now we are in the next segment of applying stress. We have studied two types of stress. What is that stress? Concentration stress. We have studied temperature stress. There is another way of the applying stress also. What is that? Pressure. Okay. If you change the pressure and delta Ng, there is no change in the number of moles on either direction. Okay. Number of gaseous product is equal to number of gaseous reactant. In that condition, delta Ng is equal to how much? Zero. Delta Ng is equal to how much it is? Zero. That means no effect. So it will not shift neither in forward direction nor in backward direction. Okay. So if pressure is increased, then equilibrium will shift in the less number of mole side. If pressure is decreased, then equilibrium will shift in the more moles side. Okay. So simple, if we increase the pressure, it will decrease the pressure. The pressure will decrease when moles are less. If you decrease the pressure, it will increase the pressure. To increase pressure, moles must be increased. It simply equilibrium will do opposite what you want. Okay. So inert gas. So inert gas volume is constant. If you add some gas, then definitely there will be increase in volume, but you are stopping it by applying some pressure or by fixing it at the volume constant. Then there is no effect, because constant concentration is number of moles upon volume. So moles of the reactant also same, moles of the product also same, volume also same. Therefore, no effect. Okay. But at constant pressure, to keep pressure constant, when you add inert gas, the volume will increase. Okay. Because when you add some more gas and you don't want pressure to increase, volume will automatically increase. Then if delta Ng is zero, like here, there is no effect at all. If delta Ng not zero, then if you are increasing volume, so more moles should increase. Okay. In whichever the direction moles are increasing, in that direction equilibrium will shift. There is another point, that is uh, presence of catalyst. Okay. If catalyst is present, it is going to affect both forward and backward equally. Therefore, there is no shift in the equilibrium, but equilibrium will be attained faster. Okay. No shift, but equilibrium attained sooner in the presence of catalyst. I think all of you understood now. Okay, as I told you, stay with me. This is the last topic of this chapter, and I am very thankful to maintain your sincerity till the last. Okay, as a thankfulness, I wanted to give you a gift of my handwritten notes. If you want that handwritten notes, take a screenshot of it, and I am writing my number and send it that screenshot to this my WhatsApp number 8171119280. Okay, save it as which chem or VB sir. VB sir chemistry. Okay. So take a screenshot of this, send it to me through the WhatsApp. Then as a gift, I will send you the PDF notes, handwritten PDF notes of it. Okay. So this is how, if you are with me, then I am with you. I am here to help you out a lot. Okay. And keep sharing my channel, keep maintaining, keep growing, keep have a good knowledge and better career. Okay, so here coming to this topic, relation between alpha, this is advanced information. So I told you I started from the very basic, that is as if you know nothing. Okay, so we are going to reach the advanced level of questions. Okay, so relation between alpha, P total and Kp. So A2, there are two types of reaction. One molecule breaks up into two same molecule, like N2O4 breaks up into 2NO2. Both molecules are same. N2O4 breaks up into 2NO2. And in that condition, this is the formula. And how it is, that you will know, the derivation is not required for the examination point of view, but still if you are interested, I will be giving through the notes. The derivation is already handwritten by me. You will get that. Okay. So AB reversible A plus B, like PCl5 is dissociating to give two different, PCl5 is giving two different products, PCl3 plus Cl2. This is example of this one. This is example of this one. Okay. So for this formula, see, if you come, careful observation. Okay. AIMS people and CSIR people, JRF people, they wanted that careful observation they want. Okay. So if you carefully observe, you will find only 4 extra here. There is no 4, rest all is same. Okay, that means when a same molecule breaks up into two same molecule, 4 is multiplied. If two different molecule, 4 is not to be multiplied. Is it understood? And there was a previous question also based upon same logic. Okay, so I think all of you understood. Now if you are carefully understanding every point of this lecture right from the beginning and keep a note of it, then you are, I think you reach to a hero state. If you are zero, okay, already hero, then it is well and good. So keep sharing, keep with me, which came. Bye bye.